Snell's law problem. I want to do an interesting one. Here we have water and air. Somebody's going under the pool with a flashlight, and we want to find a very particular angle of refraction. We're going to hit the water surface with a flashlight from underneath, and we want to know what angle it is here, the angle of incidence that makes us refract. Let's look at the Jeep story here. We can see that with the Jeep here, this tire goes faster. This is the optical pavement. This is the optical mud. So this tire goes faster, and it's going to rotate the Jeep this way. And I want to know what angle of incidence will rotate the Jeep so it goes exactly along the interface between the air and the water. In other words, having an angle of refraction of 90 degrees. Okay, so how am I going to set that up? Well, the incident medium is going to be the water, and the refractive index of water is 1.33. Air is 1.00. Fine. So let's use Snell's law. So the givens now. The given. Now we've got to be careful here. This is all the incident stuff. N1 sine, I'm sorry, let's put down the givens properly first. So N1 equals 1.33. Don't get that confused. It's the incident medium, and water is the incident medium. All right? Theta I is what we seek. N2 now is air. That's 1.00. And theta R equals 90 degrees. Okay, so now let's put that in the formula. N1 sine theta 1 equals N2 sine of theta 2. Solve that for this, which means N2 sine theta 2 over N1. So when we do S and S, N2 sine theta 2 over N1 equals the sine of the angle that we seek. So N2 is 1.00. Well, sine of theta 2, what is the sine of 90 degrees? Maybe some of you know this. So 90, take the sine of it. Dude, it's 1. All right, so 1 times 1 here, that's not so bad, divided by 1.33, and that's the sine of the angle we seek, the sine of the angle of incidence that would cause us to refract at 90 degrees. So what do we have? Really, we enter 1.33, take the reciprocal, the 1 over x key, and then press inverse sine. It's rather simple. But what that's telling us is that theta I equals 48.7 degrees. And that is special, because this angle then is the angle where refraction is now exactly along the interface. What happens if I exceed that angle? Well, if I exceed that angle, it cannot refract down into it. Refraction only occurs at a medium, remember. And if it refracts down, it was never in the medium, so it can't refract down. It obviously can't refract up. So I like to say, in this case, we're sort of backing nature into a corner. When you back nature into a corner, you might expect some odd things, and this is no exception. This is one of the more odd things you have. When this occurs, first of all, this is called the critical angle. The critical angle is the angle of incidence that causes the angle of refraction to be 90 degrees. Now, why is this so special? Why do we really care about the critical angle? Because I assure you, we really do. This is important. When you exceed the critical angle by any amount, you get a special event. So let me redraw this. air, water. All right, now I've exceeded the critical angle here. Here's my normal. All I have to know is that this angle down here is greater than 48.7 degrees. You can tell this angle is greater than 48.7 degrees. No light, nothing escapes here. In fact, all of it is reflected here. So why do we care? Well, in a normal reflection, something like 86% of the light is reflected. Not the case here. All of the light is reflected, and this is known as total internal reflection. That means no energy is lost in this interaction. All of the light reflects off. This becomes a perfect mirror. And could we use something like that? Well, as a matter of fact, we can. In our fiber optic cables, we have a cable and we have let's just call this optical mud here and optical pavement here. And what that does, anytime a ray of light gets up above here, it is bent back down into here. Any ray of light that gets here is bent back down into here. And this will allow a beam of light to travel a tremendous distance with no significant loss in its energy. The only loss that it gets traveling through this, which is known as a fiber optic cable, the only loss occurs from any opacity in the cable itself, and it's meant to be as clear as possible. So this can actually transmit through miles of fiber optic cable without any loss of signal. Where it used to be a cable this thick with thousands of wires in to make telephone calls, now the cable can be as thick as the lead in this pencil and do the same amount of work or more. So clearly, fiber optic cables are an important feature of today's modern society. It's what you're currently watching your movies with. And it all happens because of the critical angle. And once again, if you use the Jeep story, we could think about how that's going to work. This tire moves faster, this tire moves slower, and it would bend it down. The critical angle will be where the angle of refraction is 90 degrees for that particular angle of incidence. If you exceed that angle of incidence, there's no refraction whatsoever. All you have is pure total internal reflection. And then it obeys the laws of reflection, that this angle and this angle would now be the same. And that is critical angle and total internal reflection. Hope you enjoyed it. But before I go, let's just look at that formula one more time, because it's kind of a funny formula. This formula here ends up being 1 times 1 over 1.33. So if you take the reciprocal of the index of refraction of the incident media and then hit inverse sine, you're solved. Pretty simple. I like to keep it in this basic Snell's law formula though, because what if you're hitting something other than air? Well, then you need to go back to this formula. And it's such a simple formula, useful in every capacity, that it's always good to go back to the basic Snell's law formula. Once you get good at it, yeah, it's a shortcut, but there's not all that much to doing it the long way. Thanks.